Hey everybody, Dr. A here, and in this video we're going to be exploring an example of computing a moment about an axis. In particular, we're going to be asked to compute the resultant moment about three different axes, the x, the y, and the z Cartesian axes. But before we dive into it, don't forget to hit like and subscribe and be on the lookout for other content like this. All right, let's get started. We're being asked to find the resultant moments about each of the three axes. So we're going to go ahead and draw our x, y, z coordinate axes here together. And that's not a very nice looking line. So this is all given information. Here's going to be the positive x-axis. And then we're going to have a positive y-axis here. And then a positive z-axis is going up here, all right? And we're going to have this kind of box type structure here. So I'm going to go ahead and do my best to draw this in 3D. I have something like this. This first line is in the XY plane. This is also in the XY plane. So this beautiful little red box looking thing so far is the base of our box. And then our box is going to have a height like so. Okay, so this is supposed to be kind of like a 3D box looking thing. And let's see if I can put some hidden lines in here. There we go. All right. Alrighty, and we're gonna have some applied forces acting. I should probably go ahead and tell you the dimension lines, huh? So in the positive x direction, the box is 1 meter wide. In the positive y direction, the box is 2 meters along the positive y-axis, and then it kind of dips into the negative y-axis by 1 meter. So the whole length of the base of the box is 3 meters. It's just a positive 2 and a negative 1 along the y-axis. And the height of the box in the positive z direction is 0.5 meters. There we go. Now we're going to put on our applied forces. So on this back corner of the box, along the back edge right here, we're going to have an applied force of 7 kilonewtons. And at the base of the box, pointing up in this direction, we're going to have an applied force of 5 kilonewtons. Okay, so this 5 kilonewtons is completely in the z direction, coming up on this bottom corner. And again, the 7 kilonewtons is only in the pointing in the positive y direction, but it's acting on this corner of the box here. All right, so what we have here is we're being asked to find the resultant moments about each of the three axes, and that's referring to the x, the y, and the z axes. All right, so what we have to do in this case is look at our perpendicular distances from these vectors to each of the axes. Now I'm going to make a little note here, all right, under the solution. I'm going to say, although this is a 3D system, okay, it's clearly 3D, each force is only acting in one direction, right? So the 7 kilonewton force is only acting in the positive y direction, and the 5 kilonewton force is only acting in the positive z direction. And we saw back in some previous videos that if you either have coplanar, if you have a force that's only got 2 dimensions, or coplanar forces, or in the even simpler case like this, forces only in one direction, it can make our calculations a little more easy because we're not dealing with all three I, J, and K components at the same time. with these forces, right? Because they're only acting in one direction. So that's kind of what we can recognize here with this illustration. So let's go one at a time. Let's first find the moment about the x-axis, okay? So here's our x-axis. So we got to ask ourselves, what is the perpendicular distance between these forces and the x-axis, all right? So the first thing we can notice is for moments about the x-axis, the 7 kilonewton force is a perpendicular distance of what away from the positive x-axis? What do you think? Pause the video if you got to think about it for a second, because I'm about to tell you. It's a perpendicular distance of 0.5 meters away from the positive x-axis, right? Not positive x-axis, just x-axis in general. From the x-axis. How do I know that? Well, again, the 7 kilonewtons, it's pointing in the y direction, but notice that it's half a meter above the xy plane because it's in this top right corner right here. So it's kind of like floating above the x-axis. So what is its perpendicular distance away from the x-axis? Well, it's this dimension right here, right? It's half a meter. So another way you can think about it is if the line of action of this 7 kilonewton force is here, there's your perpendicular distance again. You can see it as half a meter. So like this 7 kilonewton meter would tend to rotate about the positive x-axis. Cause a rotation about the positive x-axis. If you want another way to visualize it, you can look at it this way. We can look at the YZ plane. Okay, so I'm looking at the YZ plane, okay? And I can, if I look at that YZ plane, here's my 7 kilonewtons. Okay, actually it's a little bit over here. Here's my 7 kilonewtons. And where's the x-axis here? Well, the x-axis is right here coming out of the screen at you, right? Right? So this little red dot right here, it represents this x-axis, and in the 2D drawing, it's coming out of the screen or out of the page. So what distance away from the x-axis is that? There's your 0.5 meters, all right? What else is causing a moment about the x-axis? Well, how about this 5 kilonewtons, right? This 5 kilonewtons right here is also some perpendicular distance away from the x-axis, and that's equal to 2 meters. All right, so I can also say over here, the 5 kilonewton force is a perpendicular distance of 2 meters away from the x-axis. So let's look at maybe a 2D visualization of that. In 2D, notice I have the XZ plane here. So I'm going to go ahead and kind of sketch that. I have Z here, and here's X. So so what do we know about oh, I'm sorry, I didn't mean to do XZ. I meant to do I'm sorry, I meant to do YZ. Draw the YZ again. Here we go. All right, so sorry, let me help you visualize that again. The YZ plane. I'm looking at the same YZ plane that I was just looking at a second ago. And what kind of distance away from the x-axis do we have here? So again, I have this little red dot right here that represents the x-axis. And where's that 5 kilonewtons? Well, it's somewhere right here, right? 5 kilonewtons. And then where's that 2 meters? That's this perpendicular distance right here, 2 meters, all right? So we need to establish some kind of sign convention. So I'm going to say if I'm looking at rotations about the x-axis in both of these 2D figures, all right, I'm going to call counterclockwise positive. All right, I'm going to call counterclockwise positive. So check this out. I'm going to say sum of the moments about the x-axis counterclockwise positive, and this is again from a 2D view, equals. Now let's look at the 7 kilonewtons first. We're going to have 7 kilonewtons causing a clockwise tendency of rotation. So we would say negative 7 kilonewtons times 0.5 meters. And then I'm going to have the 5 kilonewtons causing a counterclockwise tendency of rotation. And again, my red dot right here is like the x-axis coming out at us. So that would be plus 5 kilonewtons times 2 meters. So can we punch this through pretty easily? Yeah, we should hopefully be able to do this in our head. We would have, let's see, 7 times 0.5 is negative 3.5. And then we have plus 10. So without a calculator, I would get a positive 6.5 kilonewton meters, and that would give us a net rotation of clockwise here. Okay, so that's my moment about the x-axis. What about the moment about the y-axis? Okay, let's remember the problem said what are the moments about each of the 3 axes. So how are moments generated about this y-axis? Okay, so the first thing I'm going to draw here is where I'm going to draw my xz plane. All right, so let's say for moments about the y-axis, I can sketch, here's x and here's z. That's what I accidentally drew earlier for a second. Here's my y-axis coming out at me, okay? My y-axis is this little red dot coming out at me. Now, if I'm looking at this xz plane here, right? If I'm looking here, then what is causing a rotation about the y-axis? What do I see? Well, I'd have 5 kilonewtons for sure. That's 1 meter away from the y-axis, right? So I would have my 5 kilonewtons here, and that's at a distance of 1 meter away from the y-axis. So that's going to cause a clockwise tendency of rotation about that y-axis. What about the 7 kilonewtons? Well, notice that since the 7 kilonewtons is along this back edge, that back edge is parallel to the y-axis, right? The back edge of this box is parallel to the y-axis. So your net, even though, yes, it's a distance of 0.5 meters away from the y-axis, you can't rotate about the y-axis through this from this 7 kilonewtons, okay, because it's parallel to it. So let's think about it this way. That 7 kilonewtons in our figure here is like somewhere right here, right, coming out of the page, right, 7 kilonewtons. So even though, yes, it is a distance of, it's a distance of 0.5 meters above the y-axis, you cannot generate a rotation about that axis because it's parallel to it, okay? So we'll make a note of that. We're going to say 7 kilonewtons does not generate a moment about the y-axis since it is parallel to it. So all we're going to have is for moment about the y-axis, taking counterclockwise positive, what we're going to end up having is negative 5 kilonewtons times 1 meter, and we see that generated right here. That can go around the y-axis for sure, but the 7 kilonewtons cannot generate a rotation about the y-axis. So here we're going to end up saying this is 5 kilonewton meters, and that's going clockwise, okay? And then likewise, none of these forces generate moments about the z-axis, okay? And so let's talk about that. We have the z-axis here, Yeah, the 7 kilonewtons is over here somewhere, but notice it's intersecting. The line of action of the 7 kilonewtons intersects the z-axis. So that's not going to generate a moment around the z-axis. Also, looking at the 5 kilonewtons, yes, the 5 kilonewtons is some distance away from the z-axis, but look, it's also parallel to the z-axis. So again, not generating a moment about the z-axis. All right, so we'll make a note of that. We're going to say for moments about the z-axis, the 7 kilonewton force, kilonewton forces line of action intersects the z-axis and thus does not generate a moment about it. And then what about the 5 kilonewton force? The 5 kilonewton force is parallel to the z-axis and does not generate a moment about it. Okay, so then we would end up kind of summarizing and saying the moment about the z-axis is 0 here. Okay, nothing is generating that. So your three answers would be 6.5 kilonewton meters going counterclockwise, 5 kilonewton meters going clockwise, and 0 going about the z-axis. So again, you got to look at, think of it as a force causing a rotation around an axis. If an applied force is parallel to an axis, it's not going to generate a moment. If a force intersects directly